Hey, GM Warsaw, welcome to the meetup number 13 here in the new location. So we can start getting used to this location because official announcement, we're going to be hosting the next ETHWarsaw conference and hackathon here in Browary, Warszawskie. So we're going to have the whole place here and we're going to do a great conference and hackathon again. So yeah, 5th to 8th September, and we're also going to have a full Warsaw Blockchain Week. Already discussed with some partners that we're going to have more events, also around zero knowledge. So yeah. So today we're going to be talking about zero knowledge. So we have got two great speakers. First, we're going to have Leonid, who is from vLayer Labs. It's a freshly founded startup that is building on top of zero knowledge. And then we also have got Marcin from Matter Labs. For if someone doesn't know what Matter Labs is the company behind ZK Sync. So yeah, we're going to talk a lot of technical stuff today. We're going to dive into zero knowledge proofs, and then as always, we're going to have a little bit of networking, pizza and beers. So yeah, get ready, and without further ado, Leon, please come to the stage and let's start.
Hey everyone, my name is Leo, and today we're going to talk about arithmetization. But before going into what is arithmetization and how it's useful, let's, as a quick reminder, talk about zero knowledge in general and how it's relevant in the context of Ethereum. So in order to scale Ethereum, we decided to offload some computation to the rollups and do them in the rollups and then commit just the results of the computation. And there are two main types of the rollups. There are optimistic rollups and there are zero knowledge rollups. And optimistic rollups, the way they work is we do something, we commit the results, and then we have some time for the people to challenge us. So they can submit fraud proofs, that they can be like, hey, this result is actually incorrect, and here is the proof that this result was incorrect, and then the result gets reverted. Zero knowledge rollups, they have the opposite approach to that. Before submitting the result that might be incorrect, they submit the proof with the result. And there are some mathematical arguments that if the proof is correct and verified, then the result is also correct. So it has some benefits because there is no need for this challenge period. And the results that are submitted on chain can be immediately useful in the smart contracts, so we don't need to wait a week for the withdrawal, and they have in general better security warranties, but it comes with costs. But we're not talking about ZK rollups today, we're talking about ZK in general, and ZK is like part of mathematics, which is useful in the cryptography and in the Ethereum space, and it allows us to verify the computation. So ZK is verifiable computation. I think the name is a little bit unfortunate in this context because most of the times we use ZK, we actually are not using the zero knowledge capabilities, but we're using the verifiable computational capabilities. And when I say verifiable computation, what I mean is that we can offload the computation to some other party, the other party can compute it, and then provide us the results and the proof, and we do not need to reevaluate the computation, we just need to check some mathematical properties on the proof. But under the hood, the mathematics that allow us to do that is very complex, but allows us to do very simple things. So we cannot just like take any Python code or JavaScript code and make it verifiable, but we can just do basic operations there. But arithmetization is a technique that allows us to take complex abstract programs and compile them in a way to a set of very simple gates, we call them, but basically those are addition and multiplication operations, and then we can verify this computation. So arithmetization, to sum up, is like a compilation to a backend that can be verified in ZK. And There are different languages in ZK and there are different technologies. Today, we're going to be talking about Noir and Plonk. Plonk is a proving protocol, so it's something that it's like a mathematical and programmatic constraint, not constraint, but like system that will take our program after compilation and prove it. And Noir is a programming language in which we will write our computation that later can be proved. So without further ado, now we have some context why it might be relevant, and let's jump in. So this is the plan of the presentation. We're going to talk about the differences of verification versus computation, because they're very similar, but a little bit different. And when we write ZK circuits, and ZK circuits are like programs in ZK, I'll explain later why we call them circuits, they do verification, not computation. Then we're going to talk about the ZK execution environment. It is similar to how in Ethereum we have EVM, which defines what we can and cannot do, and assembly is our language in EVM, and that's all things that are allowed in Ethereum. It's the same in ZK. We just have like, let's say, a ZK execution environment which dictates what we can and cannot do. And then we're going to start expressing basic building blocks, because it will be non-trivial that any program can be written in this style, in this very limited ZK VM. But we're going to start from the bottom. We're going to start from building some basic blocks, and then we're going to build on top of them, and then we're going to start combining them. And then we're going to show that it is actually Turing complete, and you can actually do whatever you want, almost whatever you want, because it's limited in size, but we'll see the limitations later. And then we're going to talk about the real technologies. So initially, it's going to be about the theory behind that. But then we're going to talk about how it's actually implemented in the tooling. So we're going to talk about the Plonk gate format. And then as a bonus material, I'll show you some results from an actual compiler to show that what we came up with is not just an idea, but it's how those systems actually function under the hood. Disclaimer, sometimes for pedagogical reasons, there will be some partial truth here, just so it can be explained. But if you feel that something is no yes, please raise some questions. So computation versus verification. When we write in normal computer programs, we do computation, so we want to get some results. We want to compute something and get the result, and this result is what we're seeking. But when we do ZK, getting the result is not the interesting part. The interesting part is to prove to someone that this result is correct, that there are some properties about this result that we satisfied. For example, when we use it to verify transactions on the rollups, when we use it to verify transactions on the rollups, we actually do not need to just compute the new state root of this transaction or the new storage values, but we need to verify that we did this computation correctly and that there was no fraud in the meantime. So it is a little bit of a paradigm shift when you write those programs, because we're doing a verification, not a computation. And our result is usually Boolean, success or failure. Did it verify? Did it not verify? But computation is always part of the verification, because in order to verify something, you first need to compute it. But this has some important implications on how we write programs, because some parts are much easier to verify than to compute. So for example, as in cryptography, we have some functions that are one-way functions. It's much easier to verify the hash, the reverse of the hash, than to compute the reverse of the hash. So like, that's impossible in practical terms, but some of the things are much easier to verify, and we will show that in our code, it sometimes will be useful to compute something not inside of the circuit and then just verify it inside of the circuit. ZK VM. It's not a VM, actually, but this is how I call it for understanding. So this is what is allowed at our backend. So this is what we can do. This is what we're operating now. So we have just two operations, addition and multiplication. Addition is free and multiplication costs 1. So it's similar to how we have gas and solidity, and different opcodes have different costs. Here we have two opcodes, addition and multiplication. And the values that those opcodes operate on are all field elements. And when I say field, I mean 255-bit numbers modulo a prime. So we use modular arithmetic here, and very big numbers which are similar to the words in EVM, but they're 256 bits, so this is a little bit smaller, but it's not very relevant at this point. And our output is Boolean true or false, so we can, at the end, compare some things together and check if they're the same or no, and this is the output of our computation. And this seems extremely limited, and you think, hey, how can I express anything remotely useful using that? But this is what this presentation is about. So we'll show you how to express the basic programming concepts, and then by combining these concepts, you can actually build a programming language, and in that programming language, you can build useful software. So yeah, those operations are very simple, but the power comes from combining them. You can take the result of one of them, and you can plug it into another operation. So here you see at the first line, we did addition of two input variables, and then we took the output variable and did a multiplication. And this is our expected result. And at the end, we do the verification. So the last step can always be presented in a form of comparing something to 0. And our verification is essentially finding a satisfiable solution, and the solution should satisfy all of our constraints and compute to 0 at the end. And we do that by just assigning last step minus the value we expect it to be equals Zn, and Zn should be 0 at the end. And the important part, as I said, we can do the computation for free and only pay for verification. This is called unconstrained, and there is a keyword in Noir unconstrained, which allows us to write some code which we not pay for executing, but then we get results from this code, and those results are untrusted, and we need to verify them, and we need to put some constraints on them, but sometimes it's much easier to verify the results than to compute them in the constrained code. So here is a scheme of what's going on. So on the left, we have a program, which is not a very useful program, but it computes something. It's a program, and it's in some pseudocode. And then this presentation is how we convert this program to a set of gates. I will talk about gates now. And this set of gates can be verified. And this set of gates, to some people, it reminded the circuits, and that's why it's called a circuit. So it's like a circuit representation. But gate basically is just a building block. So how we told that we have two operations, addition and multiplication. Each operation has two operands and it has one output. So gates have wires, how we call them, how they connect to other gates. And this gate we see has a left wire, the right wire, and output wire. So each operation has the left operand, right operand, and the output of the operation. And then we connect them together in the graph. Now we see that it's a tree, but it's actually a direct acyclic graph because we can, it can be more than a tree, but we will see that on the next slide. And we will explain how we convert this program to this representation, because this representation can be proven and can be verified. Let's start. This representation is also called polynomial representation for the program. And it's called polynomial because if you just take some variables and do additions and multiplications in them, it's obvious that what you get is just a polynomial over those variables. If you simplify it, just additions and multiplications of those variables, and each program can be represented in a polynomial form, but some programs just have very, very extensive and long polynomial forms, and sometimes it's very inefficient, but we will show that it's possible. And because our backend, let's say, is a polynomial, we will start with representing the computations that are the easiest to represent, and this is computing the polynomials. So in ZK, some things are much easier than in other programming environments, but some things are much harder. So like in the normal processors, the easiest you can do is like OR some bits or XOR some bits, because this is the basic building block of a processor, the gates, and then not. Here, the building blocks are polynomials, so the simplest you can do is field addition and field multiplication, but then you need to express other things with that. And if you start to express like XORs, that actually becomes pretty complex, but we will not show how to do it now, but I think you will have the idea after this presentation. So let's start with expressing the polynomials. Let's say that our task that we're trying to prove to someone is that we know a root of this first polynomial. That we know some x1 that when added to x2 For example, let's say this x2 is a constant and squared, then it gets 0. This is not very interesting, but it shows us how we can combine the gates, and it shows us how we can compute some things in different ways. So here we can just have one addition and one multiplication gates on those two input variables. And we can see that multiplication gate can have left wire and the right wire connected to the same gate. And this is a polynomial representation of this program. But we can also present it in a different way. For those familiar with the binomial representation, this is the same as this one. And then it will look a little bit different because, yeah, this gate has, yes, this gate has this left wire and this right wire. This gate has this and that. At each gate, we have written what it actually represents, what it actually computes. And then there should be a 2 here, but you can actually multiply things by a constant when combining left and right wires. And then you can compute it with a bigger amount of gates. The computation result will be the same, but it's just showing that it's not a unique representation. And here we have a generalized representation for computing that something is a root of this polynomial. So you have constants, you have input variables, and you first do additions to get those intermediate monomials, or how they called parts of the polynomial. And then you multiply them together and you aggregate the results into a single expression. So this was the example of some arithmetization, and what we can analyze it and talk about some of the properties using those examples. First things to notice, not to notice, it cannot be noticed here, but first things to talk about is the depth doesn't matter. So it's not like we compute from top to the bottom, and it's not like this one will be more expensive than this one because this one has a depth of 4 and this one has a depth of 3. No, what actually matters is just the number of gates for us. So this one will actually be like slightly faster because it has just 2 gates, and this one will be slightly slower because it has 5 gates. And this one has how many? 2n minus 1 gates. Second property is this DAG is acyclic, as DAGs are. DAG is direct acyclic graph. And it is acyclic because we cannot take the result of something that is yet to be computed and use it in the computation. It's quite a natural property. But from that, we can express the property that we can't have arbitrary length loops. So one of the basic things you want to have in programming is, after you have an if, you want to have a loop. But here, it's kind of impossible. And that dictates a lot about how we write programs, because you can have a loop of length like 3, 4, 1,000, whatever, but you can't have a loop of length n, because those gates does not allow you to express such a loop. But there are techniques to overcome that, which are outside of the format for this presentation, but if someone is interested, I can show you later. And it can be really large, but it should be bound in size. So here, if we compute this polynomial for, I don't know, 100 elements, it will be a lot of gates, but we know the size of the circuit from the top, and it should always be like that. So in the practical programs that we write, we have millions and millions of gates, but we always know it's not, the number of gates is not dependent on the inputs. It's the same for all the inputs. So you do the same computation independent of which inputs do you get. So for example, when you think about verifying the transaction, you verify that transaction has such fields, and then you verify the transaction signature. And independent of which transaction you verify, this is always the same amount of compute. And if you have some optional fields in the transaction, you add the verification there, but then you disable it. So you still have those gates and you still pay for those gates. But it might be not understandable now. We'll talk about it later, how to disable stuff. And yeah, one non-obvious fact is that any computation can be presented in this form, but it may be inefficient. And we will prove this fact now with given examples. Actually, I'm not tracking time. How am I on time? Okay. So let's start expressing basic operations. And one of the basic operations that will show us a lot is division. But we're operating on field. We're using modular arithmetics, so we don't have like division in normal mathematical sense, but we have division in the discrete math sense, so we have modular inverse. So A is a modular inverse of B. It means that when you multiply A by B, you get 1. So like in normal division, if I take 3 and then I divide by 3, so like inverse of 3 is 1/3, that means that 3 multiplied by 1/3 equals 1. And 1 is a neutral element. So we're operating modulo P, which is this prime, and we're trying to check if A that someone gave us is a modular inverse of B. And it's not that someone gave us, it's that we know this inverse. And we can just compute this A in unconstrained code, because if someone remembers from discrete math, computing modular inverse requires you to do some powering from Little Fermat's theorem, and it's quite expensive even if you do binpow. But we can not pay for it and get this A for free from unconstrained code, and then just do one multiplication and one check to verify that it is in fact a modular inverse. So that shows one important trick in ZK, that sometimes it's much easier to verify stuff than to compute it from the very beginning. So we can do computation in unconstrained code. So this is actually like not a basic operation. We just do multiplication here to check, but it shows the trick that we will use in other operations. Second operation that we're trying to express is that x is a root of this polynomial. And as you see, this polynomial has two roots. It has 0 and 1. So we can have two correct solutions to that. I understand this might be not very interesting, but it will show us how to compute other things later. And if we want to show that x is the root of this polynomial, here is how we can express it with those gates. So for this polynomial, we first compute x minus 1, assign it to x1, then we multiply it by x, and then we check that our result is equals to 0. And we know that if this result is equals to 0, then the x was the root of this polynomial. And here is the same operation with the actual values for x equals 1. So first we compute this part, it equals to 0, and then we multiply, and then we get 0 equals 0. And if you substitute something that is not the root of this polynomial, like 2, then you'll have 2 minus 1, 1 here, 1 multiplied by 1, 1, and then it will not equal to 0. And then, what if we want to check that x is a bit, is a binary bit? We see that's actually the same operation as we just derived, because binary bit can have two values. It's either 0 or 1. So if we check that x is a root of this polynomial, it means that its value is either 0 or 1, but it cannot be any other value. So that's the same check to check that x is a bit. So if we have an input value, which can be field, which can be quite large, we can easily constrain it to be a bit using just those two operations. So now what if we want to check that x is a ternary bit? And a ternary bit is a bit that can have values of 0, 1, or 2. Well, that is a very similar task to what we did before, but it shows how polynomial computations are useful for checking set inclusion. So we can just take this polynomial, and this polynomial has zeros at 0, 1, or 2. So if x is the root of this polynomial, that means that x is a ternary bit. So now let's say we have inputs b0 and b1, and we want to check that it's a correct bit representation of x, where x is less than 4. So using our building blocks that we just derived, we can check that b0 is a bit, b1 is a bit, and then we can combine them together using additions and multiplications and check that we actually get x. Here is this written in pseudocode. So yeah, we use the operation that we just derived, and then we do a linear combination of those, subtract the value, and check that the result is equal to 0. So now we can check the equations if we have the bit representation for the value, and if the value is constrained to be under some power of 2. This is our range check, and range check is one of the basic operations in ZK. Because when you look at the code that compiler actually produces under the hood, it has a lot of range checks. because the numbers that you get, the field numbers, are not very useful because you cannot do a lot of operations on them. But then if you actually have normal numbers there, like U64, U32, they are constrained and they have range checks on them. And that's why this operation is relevant, because it allows us to have some building blocks that are much more useful than the field elements. And when we start programming, sometimes it's okay to have like operations that linearly compute some value, but it starts getting interested as soon as you have an if, and as soon as you have some branching, and you need to do something if this happens, or something else if that happens. But it's quite non-trivial how to have an if using just the arithmetic gates, because you just have addition and multiplication. And this is an example of how we can have an if. So we can constrain PE. P is like a predicate. It's the condition of this if. We can constrain it to be a bit. We can compute this predicate. And then we can compute this linear combination of P multiplied by then value plus 1 minus P multiplied by else value. And this has some interesting outcomes. So first, you see if P is 1, then this expression evaluates to then value, because in the second part, you just get 0 multiplied by else value, so it doesn't matter what is the else value. But if P is 0, then the second one is turned on and the first one is turned off. So it works like an if in terms of values, but it's not lazy. So for the normal if, you expect if the condition is true, then you execute the then branch, but you don't execute the else branch. Here, you execute both branches, and that's the only way it can be expressed that we know of. And it has some interesting outcomes. For example, if in the then branch, you check, oh, if I'm inside of the table, if I'm still inside of the array, then do something on the array. Otherwise, it's like out of bounds and do something else. But the problem is that you think that you do something in the then and that your predicate is true because you're in the then, but it's not correct because then is executed even if the predicate is false. So you can still have array out of bounds, and you need to program around it so that your ifs can execute both then and else clauses without causing any exception and out of bound errors. And it also obviously has performance implications. So if you start computing, I don't know, Fibonacci numbers, and you compute them with the ifs like that, then it's going to be nonlinear, but it's going to be Fibonacci real loops. So there are two essential types of loops in programming: constant length and variable length. Constant length is when you know that you want to do something like 4 times. And in Noir and in ZK for constant length loops, just linearize. Linearizing the loop, it's just taking the loop body and copying it n times. So if you execute something 4 times, loop is just a syntactic sugar for saying copy this block of code 4 times. But if you have a variable length loop, it's essentially a loop and an if at the end. And because the ifs are not lazy, you can't have that. So in the languages that we have available for us now, variable length loops are not possible. And sometimes you can almost overcome it with an if inside a loop, but then you still need to have an upper bound for the number of iterations of the loop. So you can have like iterate over the maximum length of the array, but then if you're out of bounds, then just don't do operations, do operations, but multiply the results by 0. Same technique as we used in an if before. So now let's go to normal operations that we have for free in the normal programming languages, but that require a lot of introductions in ZK. Let's say we want to check if A is less than B. This is it. And we'll use our bit splits that we developed before. This is obviously pseudocode, but in order to do that, we need to have range checks, and we need to know the expected ranges for A and B. But let's say we know that A and B are 4-byte numbers, so like U32, and then we will split them into bits and have those 2 arrays of bits, A bits and 2 bits, and then we will use the same technique as we used with B1 and B0 here to check that our bit split is correct, because the this first operation is done in unconstrained code, so we cannot be sure that it's done correctly. We cannot trust it. We need to verify it in constrained code. But after we verify it, we know that it's a correct bit representation, and then we can rely on it, and then we can do our comparison. If you look at the numbers bits by bits, then you see that if the first number is less than the second number, then there is a bit where on the left, it's less than the second bit, but all the bits left from it are equal. So that's what we do here. It's essentially like a linearized loop where we go bit by bit and we check that one bit is less than another bit. You can notice that we haven't developed a tooling to check if one bit is less than another bit, but it's actually very simple because you need in bits, if one is less than the other, then it means that the first bit is 0 and the other bit is 1. So you can just assert that. And yeah, so you will have 32 ifs here. Obviously, it's done by a programming language under the hood. We don't do it like that, but this is what happens under the hood. So if you do this and you get 32 multiplied by 3 constraints, don't be surprised because this is the only way to do that, and that's what it's doing under the hood. So that's what I said, that in some programming languages, on all programming languages, those operations are very easy because that's a simple processor operation, but in ZK, you need to do some machinery, but some other stuff is easy. Yeah, so now we're going to be talking about the Plonk gates. So we were talking about the simplified gate, which is just addition and multiplication gate. But in practical systems, the gates look a little bit different, but they're the same in essence. So we will just show you how those gates look in practical systems so that later I can show you the results from the actual compiler and they make sense because the compiler doesn't use those binary gates. So this is how the gate looks in Plonk. And don't be scared, this just is the left value. So it's the left wire. There is a constant here, and there is the value that comes from the left wire. This is the right wire. There is the constant here and the value that comes from the right wire. Here is the value that comes from the output wire. This is this index always 4. And this is the multiplication part. So we don't have addition or multiplication gates in Plonk. We have one gate which can do addition and multiplication, and it can also add a constant. So the whole program is a set of gates like above, and can prove two things. We can prove that all constraints are evaluated to 0, and that the copies on the wires are done correctly. Because even if all constraints are done correctly, you also need to check that it actually substituted the correct values from the previous computation to this computation. And when we look at our basic operations, so like addition in Plonk gate will be 1 on this parameter, 1 on this parameter, and 0 on other parameters, 1 on the output. And addition of constant will be 1 on the left wire and 1 on the output and this constant here. And multiplication similar, but we just enabled the multiplication part of this gate. And in general, at the beginning, I told you that addition is free and multiplication costs 1, which is not fully correct, but it's usually kind of correct in practical programs because additions usually combine together with multiplications in those gates. And because of that, the number of multiplications is a good estimate of how many gates will we have. And now we'll see some real-life examples of some real-life computations in the compiler. Those will be pretty similar, but we'll show you how it works with the actual gates. So first, we'll have a program that checks if something is a Pythagorean triplet. So Pythagorean triplet is that the sum of the squares are equal to the square of the third. And yeah, so this is the program, how it looks in Noir. We see that it looks like a normal program. So it has 3 arguments, x, y, and z, and it has an assertion with some arithmetic on those arguments, and we can check that it's equal. Under the hood, it gets split into multiple gates, and here we see the result of the compilation, which shows that the gate size is 9, but actually Noir adds 5 gates for doing Noir stuff. So the only interesting gates are 4 that it generates, and you can see what happens here. So this is the witness. We haven't talked about the witness, but the witness is a trace of the computation. So before, when we had this linear simple gates, The witness was the result, the value of the output wire after each step. And this references the witness. So for the Pythagorean triplet, initially at the witness we have our values, 3, 4, and 5. And then we have partial results of the computation, 9, 16, and 25, which is squared. Okay, yeah, we're getting to the end. And then you see that the first gate computes squared of the first parameter and assigns it to the third parameter, to this 9. The second squares the 4, assigns to 16. The third squares the 5, assigns to 25. And then they all sum together and the equation is checked. And here is how the if is computed. We will not go into all of that, but you can see that at the end, if you look at the trace, and if you follow this later, we don't have time to go through the if, but it's essentially the same as we talked before. So it first computes the predicate, and then computes the then, and then computes the else, and then takes a linear combination of this p multiplied by then plus 1 minus p multiplied by else, and it can be seen in the results of the actual compiler. Thank you for listening. If you have any questions, feel free to ask them, or we can talk after. I can give much more details. And if you're interested in doing stuff like that, we're hiring. Yep.
Questions?
So it's a simple question, just, couldn't see so fast. How much possible it is to do optimization of a program? Because I see that you can do one with many ifs, then maybe you can fill it out, and can you automate it? Is it already something which is being automated and stuff like that?
So I think there are two places where you can do optimization. You can do it on the compiler level, and you can do it in user space, let's say. On the compiler level, one of the main optimization techniques is doing lookup tables, as they're called. And so here, some computations are very complex, but they're limited in their domain and their codomain. So you can express them as lookup tables, being like, this is the correct result for this value. And this is how, for example, hash functions are implemented, because hash functions require a lot of XORs and ORs, and those are complex. But with the lookup table, you can just make some computations easier. So this is one optimization technique. But the other optimization technique that we can do, it's quite hard to do optimization now in Noir because you don't have actual profiling yet. We're working on it, and we're like figuring out how to do optimizations. But like in actual programming, you can just sometimes not like in actual programming, but here one of the optimization techniques is sometimes to verify something instead of computing something. So switch the computation to unconstrained code, and if you can later verify it with 100% correctness, then it's one of the optimization techniques. So for example, if you have RLP in the Ethereum, sometimes it's much easier to not like encode data into RLP, but to decode just some parts of the data that you're interested in.
Any other questions? No? So thank you very much, Leon. It was great to listen from you. So next up is Marcin, a protocol architect at zk-sync. Yeah. Leon took that one. So one of the reasons we invited Marcin here, he's brain behind this nice book that was distributed at ETH Denver. It's Zero Knowledge Proofs Explained Like I'm 5. So yeah, it did a really great job to educate people, especially non-technical.
Just wait for this.
Oh, will you? Okay.
So much.
Perfect. Perfect.
Does it work actually? Okay, cool. Gonna be so much better. So thanks, Łukasz, for the introduction. It's nice to see you all folks here. When Łukasz invited me a couple of weeks back, he said, "Marcin, come and talk about ZK." The whole room of people. I was like, should I? I mean, I'm not sure. I said, come on, they're humans. You should explain it to them in normal terms. So here I am, talking about why ZK is the endgame. Might have heard about it, ZK everywhere, but why? What's under the hood? When you talk to people about what is ZK, you hear a lot of quotes. It's magic. They're magic tricks. Don't look inside. And as you know, advanced technology is indistinguishable from magic. I made a mistake and I looked inside. So it's a question for you folks. It's your last chance to leave this room and think about ZK as this magic thing, or stay for the remaining 20 minutes on whenever pizza arrives, to take a little bit tour into ZK and understand some of the intuitions behind it. We'll not go that deep as Leo did, no. We'll try to stay a little bit on the higher level. There will be math, by the way. So for people who want to see math, there will be a little bit of math. But my goal behind this talk is really to talk about the intuition. That after this talk, you can continue the conversation about the ZK for, let's say, 2 more sentences rather than saying it's magic. So as I said, we'll be talking about the intuition. We'll be talking about places, how we're using it right now for L2s and what it can offer beyond that. And last but not least, we're going to look how it works. Of course, not fully, because we really have 20 minutes here. But I hope that you leave these rooms with actual passion to look more and understand, have more questions of diving deeper into. So, no one left? Okay, then let's take it away. If you were to remember just one slide from this presentation, it should be this one. The important thing about ZK intuition is that I have a proof that I know such a private input that make this function, this public input, run and not assert. So similar to what Leo was talking about, this is about verification. Imagine a function, even written in normal Python, is just a lot of asserts. 2 inputs, public and private, and just a lot of asserts. And what I'm saying is I'm giving you a proof that for this public input, this function doesn't assert. That's it. That's all of the ZK. Now, if you think about it for a second, and for concrete examples, let's say I know the pre-image. I know such private input that for this public input, this function doesn't assert. So what does it mean? It means that I know a pre-image of this hash. How can I prove that? Oh, very easy. I'm just going to give you the data, right? I'll be like, hey, here's the data, you run it yourself. But this can be large. And after this, you know the data too. In some cases, it's useful. In some cases, not so much. Or I can give you the ZK proof, a way to prove that I actually know the private input, but without revealing it. It will be small, and verification will not give you additional information. So to recap, function, public data, and proof. Now, how do we apply this blockchain? This is basically simplified L2 rollup. These 7 lines of code, 8, right? 7, okay. What happens? Imagine the public input is the previous hash and the next hash. Basically a previous block and the next block. Sorry, public. Private input is the state and the list of transactions. And what do? I check that the state is actually the previous state. I take each transaction, I execute it, and then I check that the state is new state. Simple, right? That's what blockchains actually do. And a proof of this execution, if we can wrap it into ZK, guarantees that it really happened. And if we send it to L1 and have L1 verify it, ta-da. To recap, this means I know such a set of valid transactions, because imagine this apply EVM is doing all the asserts, all the signature checks, everything. So I know such a state and such a list of transactions that move from previous hash to new hash. That is, this state transition is correct. The cool thing, I don't even have to tell you what these transactions are. So what can we do? The same way how you can think about hashing that enables blockchain. Previous hash, including in the next block. The same way ZK can fold computation. The cool thing about this is verifying zero knowledge proof is executing some code. And guess what? You can prove it too. So you can basically take the code that verifies some zero-knowledge proof, proves its execution, and take this proof, or a bunch of these proofs actually, because the interesting thing is not this. The interesting thing is this. You can take a bunch of independent computations, create the zero-knowledge proofs for them. In here, verify all these proofs. Remember, verifying the proof is just the computation. Guess what? You can create a proof of that. And you can keep going. So the same way how one hash, let's say the current Ethereum head of blockchain hash is describing all the transactions and all the state that happened on Ethereum. The same way one zero-knowledge proof can prove hundreds, thousands, millions of computations that happen. Okay, fantastic. Oh, what happened here? Oops. Okay, so to recap, why this is the endgame. So, as I mentioned, it can verify many computations in one go. You don't have to rerun them. Hell, in many cases, you can just get a proof from someone else, even someone you don't trust, and actually verify it yourself. It means you're saving yourself a lot of compute and a lot of latency because these proofs are tiny. Remember, if you didn't want to do the proofs, you could get all the transactions from there and run it yourself. And that's exactly what optimistic rollup do. The other interesting side effect that we're not actively using it, but this might come in the future, is you don't have to share the private input. You don't have to tell which transactions actually contributed or what state actually contributed to this thing. So others know that the state transition was correct, but they don't know what caused it. It enables all the interesting kinds of private validiums, by the way. And the other thing is, yes, because you're not sharing all these private inputs, you can also save a lot of storage and a lot of network. And last but not least, and this is something that you will be seeing over the next months and quarters, is this push towards synchronizing things across the chain. Basically, you can synchronize the state of a different chain with a single proof. Let me repeat that. You might be running some chain on the side, and then with a single proof, I can verify that all the operations you were doing on your chain for the last couple of months are correct. And after this, I can take multiple of these chains, and then I create a proof for that, therefore aggregating them into one and sharing them with other ones. Thank you. That's what I was looking for. Thank you. So at the end of the day, that's why ZK, the same, to recap, the same way how hashing is summarizing all of the blockchain history, ZK can summarize all the execution. Okay, fantastic. Great sales pitch, but where's the catch? So if we imagine this is the compute, this is something what Leo was mentioning earlier, this is the compute. This is the ZK proof. So basically, proving is very expensive. It requires a lot of complex tricks that compiler authors are really trying their best to hide from you folks. That you don't have to think about like, oops, loops have to be static size and they have to fit into all these things. So where we are is that roughly 1 second of compute can lead to hours of proving. But this is hours. A couple years back, this was days, if not months. So we're going orders of magnitude. If we keep going, probably in a couple of years, this will go down to seconds. And this is a place where lots of ongoing research are going. Okay, fantastic. So I hope all of you are convinced now that, holy moly, this ZK is fantastic. We should be using all over this. But Marcin, you said you're going to show us how it works. Okay, 10 minutes pizza is still not here, damn it. Okay, let's see how far we go. Ta-da! So we take computation, we change it to polynomials, and then we prove it. Easy, right? No? More? Okay. Okay, that's why we did the basics. If you did not see the book, by the way, we were distributing it at ETH Denver, and we'll probably be also giving it at ETHWarsaw if we're able to get it printed on time. You can go to this link, eli5zksync.io, here you can find a bunch of, basically the PDF of the book, plus a bunch of riddles. I think you should be able to do all of them. If not, okay, they're not mentioned. And then you will see how we're trying to explain gates using child-friendly images and concepts. But to this crowd, we have to be more ambitious. We should not stay on children's books. So let me give you a little bit of intuition. Why do we even use polynomials? Like, why do we bring these things that you learned in primary school and they're back with a vengeance? The intuition I have behind in my head is the following. Imagine a piece of paper, a lot of holes. And you are trying very quickly to check if the holes are in the right places. Let's not think for a second what right places mean. Then what you can do conceptually is you can try to fold it in such a way that only you know, so that all the holes align. If you do that, you only have to find one spot. And this spot will kind of go through all the holes. That's why in one move, you're proving that all the 100 holes are in the right spot. So remember, if even one of these holes was not in the right spot, this would not go through. So the similar concept, I know this is n-dimensional thinking. Bear with me, I know it's late. Similar concept happens with polynomials. Yeah, this is the scary slide, like, ooh. Let's work through it in like 5 simple, quick steps. By the way, this is like 7th grade. So if you have trouble with this, just raise a hand, I'll explain. If we have a polynomial, it's equal to 0 in some point A. It's actually divisible by x minus a. Remember this when you were like, okay, draw like x minus 3 times x minus 5, or is the polynomial that has like 0 points in 5 and 7, etc., right? If we make it more general, if you have a polynomial that's 0 in many places, surprise, it actually consists, it's divisible by many other polynomials like this, in simple form. And here's where slowly magic comes in. If these points are special, coming back to us folding the origami in a special way, if they are the things called roots of unity, if you don't know what this is, perfect, there's some Wikipedia Googling for you after this, then this is magically combining into this is magically folding to this nice thing. So you only have to prove this. So basically you can check that this polynomial has zeros in all these places by checking a simple division. How do you check it? Oh, easy. You pick a random point S and you check if these things are correct. So if you think about it for a second, we took one polynomial, okay, 2, fair, sorry. We evaluated it in one point. And if this matches, this means that all these points were matching. It means that all these holes were in the right place. Okay, fantastic. So we check the value in 10,000 points. Yay. Why do we even do that? Well, that's where the quickie thing is. So if you do the arithmetization that Leo described, and you put your asserts in the right places, and then you do this magic folding, and you pick the right point S. It has to be secret, by the way. That's why you have a trusted setup. That's why we use elliptic curves. And then you verify it's there. Okay? Okay? Okay. Too deep. That happens. So more seriously, because, as I mentioned, here we have only 20-minute, 30-minute talk. Remember, the important thing about zero-knowledge proofs are these 3 pieces. Public input plus proof plus function. And as a user, and most of you, I hope, will be using zero-knowledge in one way or the other. One super important thing is verify the function. That's what many people forget. That proof is only as good as the function, because it's actually the proof of this function execution. Check your circuits. I'm looking at you, L2Beat. Check the circuits. Make sure that the people who are using zero knowledge that you're depending on are actually verifying and auditing the circuit. Because if the bug is there, the whole thing is worthless. And that's it. If some of you were hoping for even deeper ZK, sorry, that will be in the next session. Next time I'm invited here. For now, I assume that everybody will be able to read the book. Everybody will at least understand the basics of polynomials. Please look up the roots of unities. This is fantastic. What we're talking about here is the beginnings of KZG, by the way. So if the KZG was like this unknown thing in the background, you just covered 20% of it in 20 minutes. So the rest is left to you as the exercise for the listener. So thank you, folks.
Thank you very much, Marcin. You're always welcomed and invited here for our ETHWarsaw meetups and conferences. Do we have any questions to Marcin about the presentation or about anything else? We've had two questions here first.
So in terms of a real life example, what's the public input when you're proving blocks and what's the private one?
Fantastic. So the public input in reality consists of around 6 or 7 pieces. It is the previous hash, the next hash. We're also usually providing some information about the system. For example, what is the pub data attached? That is like maybe some blobs commitments. What are the versions of the programs? Let's say in case of ZK Sync, what are the versions of the programs running? We call this bootloader, we call this system contract. So the way to TLDR it will be like previous hash, next hash, and some hashes related to the operating system, or like EVM details that we run. Because our EVM is a little bit different than the pure EVM. We do have a separate compiler, whatnot, because of the zero knowledge proofs. And private is all of the state, basically. It's all of the transactions, all of the, like, private inputs counts in gigabytes, many gigabytes. Because for each, one example is, when I said the state, you kind of need the Merkle path for every you touch. Right? You need the Merkle path, and you need to verify the Merkle paths, etc.
Thanks so much. The folding analogy, is this like on a high level, or are you guys with Boojum actually using folding schemes nowadays?
We are using folding and fry, but this has nothing to do with the folding we're talking here. Right? So just to be absolutely clear, this folding analogy was only for the polynomials to show you the idea of how polynomials can verify so many things in one go. A complete separate things to this, you might hear about things like folding and fry and recursive circuits, whatnot. These are separate concepts to be read and explored by you folks.
Hey, for the recursive proofs, you mentioned that it's possible to prove another proof. So do you need to have private input from those previous proofs or not?
No, because in order to verify the proof, I should be showing. In order to verify the proof, you need a function that was used, a public input, and a proof. Right? You do not need private input to verify the proof. A kind of this proof is replacing that, right? If you had a private input, you didn't need the proof. You could just like run the function.
So you mentioned that you're using Fry and KZG. That means you're mixing Fry, which was originally developed by Stark team, and KZG, which is usually associated with Plonk. Is that the case?
Yes. And the real reason is that because, yes, there are two. Actually, if you read the book, the 5-year-old book, we're actually talking about Fry and KZG. The real reason is that for normal computation, we do use Fry over the 64-bit field, over the Goldilocks field. But verifying the Fry is more expensive because you have to verify all the queues, whatnot. And Ethereum gas is expensive. So what we're doing in the final step, we're actually taking the Fry verification and create a KZG proof out of that. And we take this KZG proof, and that's what we send to Ethereum. Therefore, we're saving costs, we're saving gas on Ethereum verification.
I also have a question. How do I prove I am me? Like, how do I do KYC with ZK? Like, because like we are talking about like high level stuff or low level, depending on how to look at it. But in practice, for normal people, what will this allow? And how do I, for example, do a KYC, a simple KYC?
Oh, wow. Okay. I do not have a slide for that. If the TLDR answer, if you could represent your KYC as a Python function with a bunch of asserts, you're good. And here's what I mean. Usually KYC comes back to the fact that you have something that's signed by the trusted party. Meaning, have a passport, you have ID, you have something. And the cool thing about zero knowledge and these Python codes is you can say the private input will be the something, will be the JSON file signed by my government having all the data. And what I do inside this Python function, I check that the private input is properly signed, and I do a bunch of asserts that the public input that was provided is correct. Example would be this JSON file containing, 50 things about you from the day you were born to whatever your marital status, like all the data you can think government has. The public input is just, let's say, your name and your age. And what we do in this Python function, we verify the signature that the private input was properly signed by the government. And then we just check, assert public input name equals private input name, assert age equals age, done. And the cool thing is that you can run this computation locally on your machine, and then you provide just the proofs to others. So Exchange or someone gives you the Python function, you run it locally, you generate the proof, you give it back to them, and they can verify. Normally, I would show it better on the slides, but here I have to do with the hand.
Thank you, Marcin, for your presentation. You really tried to explain. Thank you.
Tried, okay. And failed.
I don't know. Alexander Kvaskov, FinTech Association. My question is, ZK proof for KYC and ZK proof for consensus. It is the same ZK technology, in the direct or not? Or maybe it's different.
Conceptually, it's the same. As I was showing on the slide, it's still the concept of, really the way to think about it for most people is keep thinking Python function doesn't return anything, a bunch of asserts, private input, public. But of course, when these Python functions are huge, like the whole EVM computation and verification, whatnot, you will do a bunch of optimizations like fries, like folding, like splitting it into pieces, etc., etc. Versus this is like, just 4 lines of Python, you would just swoop into the KZG or even graph 16, done, right? So conceptually the same, but, kind of under the hood, you would do a bunch of optimization.
Okay, thank you.
Thanks. I have a question. Do we have the knowledge or any research about soundness degradation where you do the recursive proofs?
In what sense?
Once again?
What would be your example?
We take some program and we do, let's say, recursive proofs. Maybe on some simple example, let's say Fibonacci, and is there like any soundness degradation there when we do recursive proofs? So for example, at the end, we have a lower security bits, less of the security bits.
Maybe. So this is the part where we're kind of getting into the cryptography, like deeps of cryptography. Everything that we were talking about here, and when you actually go deep into it, you'll see that the levels of security kind of depends also on the prime, on the field that you pick. At the beginning, it's around 250 bits, but very quickly it drops to like 100 something. I forgot the exact values. My gut feeling is that, yeah, we probably lose a little bit, but at the same time, the amount of folding we're doing, even if it's, 10, 20, 30 bits, it still leaves us a lot more remaining. But for this, you have to ask the cryptographers. That's a little bit outside of my knowledge.
I see. So my question was only is if we have any like known quantifications of that, how much is this degradation?
You would have to talk to someone far smarter than me. Thank you.
Okay, thanks.
Thank you. Any other questions? Yep, sure.
You are so sure about ZK is the end of the game. I mean, how is it possible if it is mainly depend on as a user of, ZK, it mainly, gas fees mainly depends on Ethereum gas fees. I mean, and it really hurts us as you know, how it might be the end of the game. I mean, optimistic rollup is not end of the game, and this, and last one, for which date is the snapshot of ZKC? Thank you.
Okay,
When
so coming back to
open.
your first question, it's because of this tree folding that I was showing. This allows you to take a single proof over hundreds of batches. Therefore, you pay on Ethereum once. You pay once for verification, but there could be hundreds of batches that you actually verify. This is where the scale is. So even if the verification costs you around $100 right now, if it spans over 10,000 batches, this is just a fraction of a cent per batch, which means it's even less for each transaction.
Okay, we're gonna have one last question.
Okay, so I think one of the issues with ZK is that basically the private input can be correct, but can be one of the correct inputs, right? And for example, you brought up the bridges between chains, and this is where the problem is, right? Like you can verify that the computation given this set of transactions was done correct, like the state transition function was executed correct, but it might be just a subset of transactions that were like, the consensus agreed on, or were just like random signed transactions, right? And can you expand on this problem?
Yes. So actually, sorry, I should have not closed the slides. This was a mistake on my side.
Did it die? Okay. No. This goes to the recording, so.
Okay. Wow. I think it wasn't working for a while.
Oh, it is working. It was just switched off.
Okay. So, and this is actually a very good point. And as I'm answering this for people who are not following attention, the 5-year-olds, can you figure out how much candy mom left? The idea is like you got 2 and all the animals are happy. So how much candy mom left? And it's actually a very good point. And in order to make shit, now I see everybody's counting candy. Okay, I'm gonna give you a hint. No, 3 or 4, and you don't know how much. Wow, I have attention of the whole room. Okay, or 4. The beauty of it, and this is exactly what he was talking about, is that you don't know. You got your first share of candy. You don't know how much left. And the whole point was, in the basic thing I was describing, with just public input being transitioned from previous state to next state, you hypothetically don't know which transactions contributed to it. Unless 2 things. Either you explicitly add this, for example, a rolling hash of all the transactions or a Merkle tree of all the transaction hashes to your public input, or if it's represented somewhere in the state. Then you can actually prove which concrete transactions were included in the state and participated in this transition. Everybody know that this is 3 and 4? Yay? Nay? Okay, I assume you did.
We trust that you say correctly.
Should not trust, you should verify, please.
Sorry, don't trust. Cool. Thank you very much. Again, Marcin, it was very entertaining and very compelling presentation. Big round of applause for you. So pizza's here. So it's going to be served with the drinks at the foyer at the entrance. So if you guys want to move out over there, we're going to have some time for networking. And yeah, hope you enjoyed the meetup today. Thanks,